Welcome everybody. I still see people coming in, so maybe we wait a few more seconds. I can already say that this session is going to be recorded, so please take note of that. And what I can also say in terms of the procedures is that we encourage you that you ask questions via the chat. We will collect these questions for the question and answer and discussion session that we have just after the two presentations at the beginning. And if there's time towards the end, or if there's an clarification request that needs to be kind of orally, you could also raise your hand with the tool and then unmute yourself, but the chat is the preferred thing. Okay, having said this, we start with the third webinar of the circular project. Today we have two speakers. First speaker is going to be Dr. Daniele Castello of Aalborg University. Daniele is associate professor in the Department of Energy at Aalborg University, and he's leading the upgrading work package in the CIRCULAIR project. And the second guest speaker today is Dr. Jens Anders Hansen of TOPSOE. Jens is a lead scientist at TOPSOE and has more than 3 decades of experience in catalyst and process development. Okay, and what I want to do as well is a little bit of advertisement of further webinars and events of the CIRCULAIR project. You can follow our LinkedIn page and our website to be aware of these events, and very particularly we have an industry workshop, also a remote workshop, and the 28th and 29th of January next year. Okay, then I hand over to Daniele for the first presentation.
Yeah, thank you very much, Tino, for the nice introduction, and good afternoon to everyone. My name is Daniele Castello of Aalborg University, Denmark, and today I will have this short presentation about the activities in the CIRCULAIR project regarding the upgrading. So upgrading of HTL biocrudes from agricultural waste, from pretreatment to innovative processing solutions. So I will basically present this topic, touching mainly 3 points, which will be corresponding to the challenges in the biocrude upgrading. So the pretreatment of biocrude, the fixed bed processing, and some innovative approaches to the upgrading of the biocrude. Let's first state what is, let's say, the big picture. So in CIRCULAIR project, we deal with agricultural waste, manure, straw, and their mixtures. And this is based on HTL, so hydrothermal liquefaction, that basically is a hydrothermal technology to convert this biomass feedstock into biocrude, which is basically let's say a carbon-rich liquid, and it is the base for the production of biofuels. The concept foresees that we start them from the biocrude, and then we operate hydro treating, so reaction with hydrogen at high pressure and temperature with a catalyst to upgrade this biocrude into basically a mixture of hydrocarbons that can be then distilled to produce the different fuels that we use. Mainly in CIRCULAIR project, we target jet fuel production. This is basically the conceptually what we would like to do. However, in, let's say, the application in reality is not straightforward, in the sense that there are some challenges. First of all, the agricultural waste, when they undergo HTL conversion, of course, they will produce a biocrude, but this biocrude is not cannot immediately be utilized for the upgrading. Here we see that the product, raw product coming from HTL reactor is often a mixture of biocrude, char, so the solid product, aqueous phase, and of course this depends a lot on the separation that is adopted on the HTL plant, but in general, the product directly from HTL is not ready immediately to be upgraded. And in particular, this product has some kind of similarities with so-called oil sands, so mixture of the multiple phases. And what we thought is that we can actually build on the existing knowledge on this topic in order to approach the problem of the upgrading. We need, in particular, we need pretreatment to treat this fraction, and we need pretreatment for a simple reason, because I mean typically the upgrading, so hydro processing, is operated in a fixed bed, trickle bed reactors, packed with a catalyst. And so this oil should be at least at a minimum quality that can be processed in this kind of reactors that are those used nowadays, are normally used in refineries. And this means that biocrude should not contain solids, which must be separated, and very importantly, cannot contain inorganics, which can actually poison the catalyst, and they should be contained ideally to levels of, let's say, preferably less than 50 ppm, but let's say in the order of a few hundred ppm. This actually is an issue, and how to achieve this in practice is something we struggled in our research, and we think we found some possible solutions. We elaborated a concept that is composed of a phase separation first, so first extraction of the biocrude from the bulk using a solvent, and then with this, once aqueous phase and solids have been separated, we can actually perform demineralization to reduce the inorganic content. And we see some ways we explored. First of all, the solvent extraction, we elaborated a procedure based on acetone extraction. Acetone extraction followed by decanting. And we tested this on two different biocrudes in this project. One obtained from 50% manure and straw, another one from 100% manure. And we actually, we saw that from the raw product from HTL, we were able to collect around between 50 and 40%, between around 30% of biocrude that could be extracted from the solid matrix. So this actually resulted into a visible change in the sense that from basically a mixture of solids, we ended up obtaining something that is more like a liquid viscous product. However, this only tells, let's say, part of the story, in the sense that this after this filtration, still the oil content, the biocrude had a significant level of ashes, especially, so inorganics, that was in the order of a few thousand parts per million. So the problem at this point was how to reduce this. And we tested two ways. One is the acid washing, which is, let's say, the state-of-art solution, washing the biocrude with a wet aqueous solution of some acids, and we tested some of them. And let's say a novel solution, which is based on adsorption. So trying to remove this inorganics by adsorption on a solid material, which is a way that it is less let's say, innovative in the field, at least of HTL biocrude so far. And here is a summary of the results that we obtained by comparing these two approaches. And we saw, I mean, quite variable results, but in general, let's say all the treatment, especially with the strong acids like sulfuric acid, resulted in some reduction in the ash content of the biocrude. And also one thing that was quite remarkable for us was that the utilization of solid sorbents also resulted in a very important reduction, especially using some materials like alumina and silicoaluminate. This actually, and also brought to a comparison of the two technologies, also in terms from one side of ash removal and from the other side of carbon recovery. Because of one of the problem in this pretreatment is that, of course, once we expose the biocrudes to these procedures, we are losing some of the organic contents of organic carbon, which is something we want to avoid. And we compared the different technologies, the different basically approaches in these terms, and we found that basically the treatment with sorbents is quite beneficial in terms of ash removal, and in general, in most cases, also can retain more carbon inside the biocrude. And this is also important because the acid washing has a drawback of basically losing some carbon in the aqueous phase that is in the aqueous solution that is used to wash the biocrude. And so we found out that this treatment with sorbent can be both effective and prevent reduce to some extent the carbon losses. In any case, biocrudes should be treated before hydrotreating. We also performed, thanks to our partners, Eni, some characterization of the products before and after the treatment, the demineralization, and actually we found relatively negligible differences. In some cases, the treatment resulted in a reduction of some of the light nitrogen-containing compounds, both for acid and sorbent wash, with a prevalence of the acid wash. And here you can see some of the TICRMS results elaborated by our partner Eni. These results were also summarized in a public deliverable from the project. Once, let's say, after the pre-treatment, another thing, of course, that is challenging is the actual processing. So the upgrading to reduce the oxygen and nitrogen compounds, and basically converting the biocrude into a mixture of hydrocarbons. Here we took an approach here in Aalborg University based on a fixed bed hydrotreating, and we started from this 100% manure biocrude. And we just performed a filtration, so we extracted the oil part, but we didn't do the demineralization because, I mean, we are working here at a bit higher scale, so around, let's say, 10 kilos batch. And so we started from this biocrude, quite heavy. You can see here the microcarbon residue is quite high. It's very far from a jet fuel, of course, composition. So the upgrading is pretty much necessary. We operated with our lab scale plant, continuous hydrotreater. It's a relatively small plant with a throughput of 30 milliliters per hour. And is composed of 2 reactions in series. And what we thought is a multi-stage approach. This campaign was actually divided into 2 branches. First one we call viscosity reduction. We just processed the biocrude over a catalyst bed constituted by hydrodemetallization catalyst to remove the residual ashes, and a minimum activity NEMO catalyst at low temperature to basically stabilize the oil and reduce its viscosity. And the product from this were processed in a further 2-stage architecture with more, let's say, with increasing temperature, 340, 400 degrees C, and a choice of catalyst that becomes, let's say, more to the higher activity nickel molybdenum catalyst. We are speaking in all cases of sulfided catalyst, and they were provided by our partner TOPSOE. In short, the first part of the campaign, I would say, it was this stage at mild conditions, low temperature. It was a stage that didn't imply a visual change of the properties of the oil, but nevertheless, with the analysis, we could see that these mild conditions were effective in reducing the ash content. First, and especially in abating the microcarbon residue of the oil, so also removing the heaviest compounds. while the composition was not really affected in a particular way. This actually is a stage that is crucial for the subsequent step that was operated at higher temperature, and actually ensured the success of the second one. After the second stage we presented, here instead we saw the actual apparent change of the properties of the oil. You can see, I mean, the dramatic decrease in density and microcarbon residue. You can also see visually the appearance is different. And here we obtain an almost complete oxygen removal and below 1% nitrogen percent in the resulting product. So the second part was actually the one bringing the actual removal efficiency, but it was actually made possible by the previous viscosity reduction step that ensured very smooth operations. We managed to run for a few hundred hours on stream. Of course, the upgrading resulted also in a apparent change in the boiling point distribution. We could see that after the basically stabilization step, the oil is still relatively heavy. This is a simulated distillation graph, boiling point distribution. And after instead the further treatment, we arrived to around 29% products in a range under let's say kerosene range intended between 175 to 150. So with quite of an increase in this available fraction. At the same time, we have still a large part of the oil in at the higher boiling point fractions that could be potentially used with potentially undergo hydrocracking or isomerization treatment to increase even more the part of jet fuel compliant compounds. This was basically the fixed bed hydro processing. I would say that this is, let's say, the state of the art in the field. So that is the standard way of approaching. But within the project, we also have another set of activities which want to test slurry hydrotreating, and this is the work carried out by our partner RISE from Sweden. Basically, so the trickle bed, we just say, is fixed bed shaped catalyst. It's actually can be challenging for biocrudes because it's prone to coking. So it's easier, let's say, to have coking and clogging of the units. And so the feed, as I just said, I mean, needs to be pre-treated and needs to have some specification to enter the process. The slurry process is more tolerant, I would say. Here, basically, we are dispersing the catalyst inside the biocrude, and is more robust for these thick oils. It normally is used in refineries as a bottom of the barrel solution to upgrade, let's say, the heaviest fractions of the biocrude. So we wanted to test this also for the HTL biocrude, and there were some tests performed at RISE. In particular, the big problem is would be to run with a raw product from HTL, and which is full of inorganics. And one solution that was found was that of using a so-called sacrificial catalyst, basically a bauxite slag. And which actually can trap the inorganics and at the same time, let's say, promote the formation of more liquid products from the semi-solid bulk that we feed to the reactor. Some tests were done also here with different concentrations of the bauxite, 375 or 120 degrees C. And here you see basically some of the collected products. And remarkably, we were able to move, let's say, most of the inorganics into the solid residue, leaving a relatively, let's say, low ash heavy oil that can be further processed. So in the end of this, let's say, short presentation, I would like to highlight a few take-home messages. So that are important for the development of HTL. First, beware of the interface between the HTL and upgrading, because the biocrude needs pretreatment before the upgrading, and this is a delicate part of the process to ensure, let's say, smooth operations in the hydrotreaters. The multi-stage trickle bed is an effective strategy for the upgrading of biocrude. It's important to remark that each stage has a specific scope, so because the reduction, the oxygenation, denitrogenation, and so on and so forth, and the conditions and catalysts must be selected accordingly to the scope of each stage. Finally, the slurry hydrotreating is a promising approach because, as I said, this is biocrude is a heavy product with inorganics and so on. So this can be a viable approach. There are some ways, like for example, the dispersion of this heavy biocrude into some carrier can be an option we are also testing. But we got encouraging results with the use of sacrificial catalyst. So just some acknowledgements to all people that collaborated in this project and has contributed to all of these results from all the partners. You list here is a kind of a teamwork from several people. So I'd like really to thank all the partners in the work package, and of course thank you for the kind attention.
Thank you, Daniele. So with that, we come to the second presentation by Jens. So Jens, maybe you can start sharing the slides from your side. And let me repeat what I said at the beginning. So please, if you have questions to the presentation, use the chat to raise them, and we will then, afterwards, use all the inputs to the chat in order to have the discussion with both Daniele and Jens. Okay, Jens, you're still muted and we can still not see your slides.
Now you can hear me, I think.
Yeah, you're unmuted, but please share again.
Can you see my screen now? No.
We see a screen now, but it's not yet the presentation.
It's the presentation. Okay.
So it's good that we have a question in the chat. Maybe while you start sharing, we can have a first question to Daniele, and it's about the slurry hydrotreating. And you can read it by yourself. So if this sacrificial catalyst has been optimized to different feedstocks, yeah, and then if there would be other options. So maybe we answer that afterwards in the discussion section. So you have 20 minutes to think about it. And now we can see your screen, Jens, and,
yes.
and maybe you start with your presentation.
Thank you very much for the introduction here. So this presentation deals with how to upgrade the pyrolysis oil derived from sewage sludge into sustainable aviation fuel. And here the topic is how can we produce sustainable aviation fuel from sewage sludge derived pyrolysis oil. And here is the outline of my presentation. I will say a few words about TOPSOE, then I will discuss with you commercial jet fuels and specification for jet fuels, and then I will come to upgrading of biofuel, and then I will have some examples where I demonstrate how you can upgrade pyrolysis oil derived from sewage sludge to sustainable aviation fuel, and then a few take-home messages at the end here. So TOPSOE is a company formed in 1940 by Dr. TOPSOE, and it's based on two things: a passion for science and a determination to make a positive difference in the world. And we stay true to this legacy today, and our purpose is formulated in the wording "perfecting chemistry for a better world." Okay, the status for TOPSOE now is that 1/3 about 1/3 of the current renewable diesel and SAF operating capacity worldwide is based on TOPSOE technology. So yeah, we have a broad knowledge about how to convert feedstock into SAF. Let us take a look at jet fuel specifications, and I mean, Daniele also addressed this to some extent, and I will go a little bit deeper. And when you have a jet fuel, I mean, the goal is to provide a fuel that would never be a problem for a turbine engine or an aircraft. That's a statement from a founder of a company called Aalborg. So there is, of course, a lot of conservatism when you are flying. You need a fuel that is able to work and bring you from one place to another in a safe manner. There are specifications in play for jet fuels. There are the standard fossil-based specification D1655, and then there are other specifications where you have synthesized hydrocarbons. So we cannot just convert biomass to jet fuel and without having a permission to use it, and that can be a lengthy process to get a new feedstock approved for use as jet fuel. And here are a lot of different properties you have to meet when you are producing jet fuel. I will not go through that in detail. All jet fuels must have a decent smoke point, and that will be important for my presentation. And I will look more into the smoke point, and the smoke point has to be 18 if you have a low concentration of naphthenes, or minimum 25 if you have a high concentration of naphthalene. Flash point is very important. The flash point should be minimum 38 degrees C. Then the freeze point should be between -40 and -47 degrees C, and you can say the freeze point is depending on the nature of the molecules you have in the jet fuel. So freeze point is a function of the molecules you have present in the jet boiling range, whereas flash point is more a distillation kind of properties. So if you are distilling in the right way, you will normally be able to meet the flash point. But freeze point can be tricky to meet and can require that you do isomerization of the product. There are specifications about the boiling point range, viscosity, density, and so on. And sulfur concentration, well, it should be max 0.3, and aromatic should be max 25%. And this is something that is not so difficult to meet when it comes to ordinary fossil fuels. Then if you add something different, synthetic components, then there are further requirements you have to meet. But basically, smoke point is very important here, and you will see that later. Then a few words about synthetic blending components. There are various processes where you can produce these blending components, and you can also find specification for those, and you can see that the nitrogen content has to be max 2 weight ppm. You can see sulfur also is very low compared to what you see if it's fossil-based jet boiling components. You have halogens maximum 1 milligram per kilo. So you have very stringent properties here you have to meet, and I think coming from a fossil world, this is very low values. But these components here are synthesized. They could come from Fischer-Tropsch wax or other very clean feedstocks. So this is showing very low values for contaminants. And this is something I will discuss with you, because that's more difficult when it comes to use of third generation biofuels. Then let's take a look at biofeedstocks. If you look at first and second generation feedstocks, then it's virgin oil, it's waste oil and fats, and they are primarily paraffinic. They are not so contaminated, and you can produce by hydroprocessing. You can produce, let's say, synthesized jet range products, SAF products. But if you look at solid waste and rotational crop, that's third generation biocrudes. Then you have the pyrolysis process. You can pre-treat the oil from the pyrolysis process to remove some of the contaminants that could be metals, and then you can hydroprocess to meet the requirements when it comes to specification. You can also go another route. You can gasify it, and then you can produce a syngas. You can do Fischer-Tropsch, and then you can do hydrocracking, and then you can produce jet fuel via that route, and that's allowed. You can do that, and that's within the ASTM specification. You can use jet from these sources and blend that with fossil jet, and you can fly on that. But when it comes to pyrolysis oil, you have to demonstrate that the jet fuel you produce is okay, and this is a work that I think is ongoing for many of these processes, because today you cannot do it because of that you need a permission to use it. But hopefully we can develop technology so we can use jet fuel from those processes and be able to use that as a jet waste material together with fossil fuel. So let us take an example here. If you look at different biofuels compositions, you have the soybean oil, which is very, very pure. It has hardly no contaminants, very low sulfur, very low nitrogen contents, and it has a high hydrogen to carbon atomic ratio. And if you have a hydrogen to carbon atomic ratio higher than 2, you have paraffins, basically. And when you remove the oxygen, you will end up having triglycerines having a paraffinic structure. And if you dewax, if you take the oxygen away and you dewax that, then you have a jet that is acceptable for use in commercial jet planes. You can also look at crude tall oil. Again, you can see a relatively high hydrogen to carbon ratio. That's 1.73, and this is also paraffinic in nature. It's more contaminated, so it has higher sulfur content, it's more nitrogen, and you have higher impurities in general, so this is something you have to take into consideration. When you look at sewage sludge-derived pyrolysis oils, as we will look at in this presentation, you can see that you have a much lower hydrogen to carbon ratio, that's 1.4. You have not so high oxygen content as you have in soybean and crude tall oil. You have much more sulfur, and you have an enormous amount of nitrogen. Really, really high amount of nitrogen because it's coming from sewage sludge. And it's far higher than what you see in fossil-based fuel. And when you have to produce high-quality jet, you basically have to exclude everything else than hydrogen atoms and carbon atoms. And then you have to be sure that the hydrogen to carbon atomic ratio is 2 or higher. So when you look at these feedstock and compare with the quality for jet, you can see that you need to add hydrogen to the oil before you are able to have a product that will have a sufficiently high hydrogen to carbon ratio. I talked about smoke point before, and here I have some data from fossil processing, and this is from TOPSOE testing here. And what I have shown here is the smoke point as a function of aromatics boiling in the jet range product, and you can see smoke point will increase if the content of aromatics drops or decrease. So you need to remove aromatics in order to have a high smoke point. You can also see on the right hand side that here I have plotted the atomic hydrogen to carbon ratio against smoke point, and you can see when the atomic hydrogen to carbon ratio increases, the smoke point increases. In fact, if you have pure paraffins, you have smoke points very, very high, exceeding 40 or even higher if it's a pure paraffins. So the smoke point is a function of the molecular composition. And therefore, when you convert biomass into jet range product, you have to be sure that the atomic hydrogen to carbon ratio is high. Otherwise, you cannot meet the smoke point requirements. Then let us then go to how can you upgrade the pyrolysis oil derived from sewage sludge. And Here I have listed the elemental composition. You can see the high nitrogen content, 8%. That's a lot, and you have to remove all the nitrogen. And you can see here the DC-DC programmer that we can look into what kind of components do you have in the sewage sludge, and then you can study as you upgrade it. You can see which of these components are being removed and what are you forming. And this is a presentation in itself to go through that. So I will skip that, but I'm just saying that this is what we do when we follow the fate of these molecules. We use DC-DC a lot, and we have a collaboration with the University of Copenhagen, and we have recently issued papers showing about how to characterize sewage sludge and also products from sewage sludge in molecular details. Taking a deeper look into sewage sludge, here I have shown contaminants present in sewage sludge, and sewage sludge is heavily contaminated. You can see we have arsenic that can come from food. It can also come from other sources. We have iron that can be high or it can be low. It depends on the batch of sewage sludge you look at. You can see a very, very high concentration of silicon, ranging from 200 to 460 weight ppm. You can see chlorine present. You can also see fluorine present. And fluorine is, we have seen that this fluorine is coming from PFAS. And PFAS is, as you all know, around. And PFAS is fluorine compounds that are very, very difficult to remove. And that is something that could be problematic for upgrading this to jet product, but I will come back to that later. So we have all these contaminants, and you have to get rid of all the contaminants. They are not allowed in the jet fuel. I can go a little bit. So the silicon is originating from cosmetics and other pharmaceutical stuff. So silicon is something that come into the sewage sludge because human beings are using cosmetic products. And silicon is not nice for a catalyst. Arsen is not nice for a catalyst either. So this is something that is important to address. So what we have done when we convert this type of biocrude to transportation fuel is that we first have to stabilize the feedstock. That was also mentioned by Daniele, that stabilization is needed, low temperature stabilization. Then we have to use a catalyst system, so we remove the contaminants. And then when we have removed the contaminants, then you can really start removing oxygen, nitrogen, and sulfur down to a very low level. And then you have a product that goes to separation, and you can fractionate that by distillation. You have the light gases, you have the hydrogen, you have the ammonia from the removal of nitrogen, you have the sulfur as hydrogen sulfide, and then you can, depending on boiling range, you can convert. You can have a naphtha range product that could go up to 150 degrees here. Then you have from 150 to 300. You have the jet boiling range, and the question is that sustainable aviation fuel meeting the requirements needed? Then you can have some product that boils higher than jet, and that was also what Daniele showed. Some products were boiling higher than jet, and then you could take that back, and then you could hydrocrack that, and then convert the heavier material into more jet boiling material, and thereby you could optimize the amount of jet you can produce. So this is one of the routes we have pursued in our testing here. And then I have a slide here showing what we have done. We have a pilot unit with either 1 or 2 reactors. The 2 reactors are in series here. You can see that that's reactor 1 and 2. Then you have separation, and then you have oil that has been hydrotreated. You have water originating from removal of oxygen. You have a gas. So we have done a lot of test work on the pyrolysis oil derived from sewage sludge. We have done testing with 1 reactor. We have done testing with 2 reactors, and we have used 4 different pilot units. And we because the process I showed before, we have stabilization, we have guard catalyst, we have hydrotreating catalyst, and we only have a unit with 1 or 2 reactors. So it was difficult to do everything in one go. So therefore we were processing the feedstock, collected the product, and then we were using the product as feed in another test. And that was also the approach taken by Daniele, that product was collected and then used in another test. So we spent a lot of test hours and did a lot of pilot testing in order to figure out how to operate this pyrolysis. The first experience in our testing was, well, we need to stabilize it, and we figured out that if we use a too high temperature, we had the reactors plugging, so we have to find a temperature that was able to stabilize the feed, but without plugging the reactor. So this means that we have to use a low activity catalyst. And in this testing, we looked at a one-reactor setup where we investigated variations in space velocity, temperature, hydrogen to oil ratio. And in general, if we find the right operating window when it comes to temperature, we were able to reduce the MCR up to 60%. And we saw an increase in reduction with increase in temperature. It was not so much a function of space velocity. Also, some sulfur, oxygen, and nitrogen was removed. It was easier to remove sulfur than oxygen than nitrogen. Contaminants was reduced not so much at these low temperatures. You could see removal of chlorine started at 220 degrees C, and in fact we had a low deactivation rate. We tested different batches, and some batches were easier to stabilize than others. And we could see that if the MCR was high, we have to be a little bit careful about not selecting at too high temperature. So we did a lot of work to figure out how to stabilize it. We collected product from this, and then we looked into hydrotreating. And here I have shown two approaches. In the first test we did, we had a stabilization catalyst in the first reactor and a treating catalyst in the last reactor. And this is the green point here on the graph to the right, where we have shown the sulfur content in the product versus 1 hour. And next to the numbers, you can see temperatures 330, 340, 360, and 380. That was a temperature of the treating reactor. And you can see here that the sulfur content increased a lot. And even when we increased the temperature, we saw a drop in sulfur content in the product, but you could see that the sulfur content was far higher than what we wanted it to be. And normally we can test without guard catalyst when it comes to fossil applications, but here it was very crucial to use a guard catalyst. So in the next test, we installed a guard catalyst on top of the treated catalyst in the second reactor, and you can see now with the red dots here that now it was much easier to remove the sulfur because the catalyst was not deactivated by contaminants. So it's very crucial that you have a guard catalyst system here, and with a high amount of contaminants present in this feedstock, you need a lot of guard catalyst here. And in a testing where you only have a limited amount of catalyst volume, you will see a faster breakthrough compared to a situation where you could use a larger amount of guard volume. So this clearly indicates that the guard catalyst system is very crucial. We did also test where we started the guard catalyst system here, and especially silicon is a problem, and silicon was present in concentrations higher than 200 reg ppm. And we have those silicon compounds. These are polycyclic silicanes, and they are found in cosmetic products. So they are regulated from cosmetic products, and these molecules they are treated by the guard catalyst system, so the silicon is trapped in the guard catalyst system here. Arsenic is also a poison, and that needs you can say a tailor-made catalyst for capture arsenic, and silicon needs another catalyst to be able to remove it efficiently. So a lot of silicon, and I have now we're talking about jets. So I have estimated that in order to produce, well, if we're dreaming that we can use the SAF from this sewage sludge in 100% amount. This is not allowed, but let us assume that we can do that. Then I have calculated that if we want to fly from Copenhagen to Bangkok, then at one-way flight, a daily flight from Copenhagen to Bangkok, then this will consume about 80 tons of jet fuel. And if we process 10 tons of pyrolysis oil per hour, and we do that for 6 months in order to fuel this plane from Copenhagen to Bangkok one way, then we, for a 6 months period, we have to trap close to more than 10 tons of silicon. And you can also see the amount of arsenic here. So we can see that this pyrolysis oil is heavily contaminated, and you have to remove a lot of silicon in order to be able to process this. And this is only one flight, so you can imagine how much guard material you need if you want to fuel more than one flight. So a lot of guard catalyst is needed. It's not a problem. Of course, it costs to have more guard reactors and also use guard catalyst. But it's possible to trap it, and if we raise the temperature, we can trap more. So it's not a problem from a technological point of view to remove the silicon. Then we did some testing, additional testing, and here what you want to do is that you want, after guard catalyst, you want to do the deep hydrotreatment, so you will remove oxygen to sulfur and not into the compressor level. So what we did was we did a first test where we produced the feedstock, and that's the feedstock listed in the table here. So the first step resulted in the feed having a nitrogen content of approximately 4,000 weight ppm nitrogen, and the feedstock had a concentration of about 80,000 weight ppm nitrogen. So it was attractive to do it in 2 steps. So we removed the ammonia. Most of the ammonia we produced from the nitrogen, we removed that in the first step, and then we produced a feed, and the feed properties here are those having 4,000 weight ppm nitrogen. And then we did the second hydrotreatment process here, and then we obtained a product here. This is what we call the total liquid product, the TLP product, and you can see here now we have a nitrogen content close to 100 weight ppm. Sulfur is below 2 weight ppm, aromatics below 22.9. And then from this product we isolated a jet boiling range product, and you could see that the nitrogen content in this was 65 weight ppm. You can see the aromatic content was 22.6 weight percent, and you can see that the smoke point was 22.3. And if you look at a jet spec, we don't have any jet specs available for this process route, but if we look at what is used for synthesized jet boiling range compounds, you have to be in a density range between 0.77 and 8.4. We were meeting that. Sulfur has to be below 2. We were meeting that. Nitrogen has to be below 2. We were not meeting that. Aromatics was below 25 volumes, and we were meeting that. And smoke point, we were higher than 18. But you can see here, nitrogen is very, very difficult to remove, and we were not able to meet that in this test. Then we did another test, and here we produced, from another test, we produced a feedstock having a nitrogen content of 6,000 weight ppm, and then we treated that, and we used different operating conditions from operating condition 1 to 4, and you can see in condition 1, we were having a nitrogen content that was 26 weight ppm, and that's higher than 2 or 1. Then we raised the temperature, kept the pressure the same and space velocity the same. Then we were able to remove nitrogen down to a level below 1 ppm. And then you can also see other properties. If we raise the space velocity and the temperature, we are still able to remove the nitrogen down to a level that is below 1 ppm. If you reduce pressure, it was more difficult. But you can also see fluorine was really a problem here, because you can see that the fluorine was higher than 1 weight ppm here. So this is just saying that we removed some of the fluorine, but you were not able to remove the fluorine down to the requested level less than 1 ppm in this test here. And then we looked more into how can we remove the fluorine down to a level that is below 1. And then we looked into the product quality of the jet fraction here, and here are some numbers. And this is showing the fluorine distribution as a function of boiling point. And you can see, in fact, the highest fluorine content was found in the lower boiling fractions, not in the higher fractions. And you can see that when you have a boiling point exceeding 200 degrees C, then you have a fluorine content lower than 3, in the range from 200 to 225, but higher than 225, then it was lower than 1. So you could see, well, the lighter part of the jet has a high fluorine content, but the heavier product has a lower fluorine content. So what we then figured out was that you could use hydrocracking to produce a jet with a low fluorine content. And here is a slide showing what we did. So what we did was that we have the guard catalyst in the first stabilization catalyst, then we have the guard catalyst, then we have the first removal of hydrogen of H2O, and then we were taking the product from this without nitrogen being present, and then we converted that in a reactor named 13C, where we removed the nitrogen down to a very low level. Then we fractionated the product, and then we recycled the diesel product, the product boiling higher than jet. We recycled that to a hydrocracking reactor named 50, and by converting the heavier part into the heavier part having a low concentration of fluorine into jet, we were able to produce jet that has a lower jet content than so we could meet the specification. And then we had this split where if the light jet, we could maybe route a little bit of the light jet into the combined jet to obtain the right fluorine content. So this was the one way to cope with that fluorine content. Another way was investigated a little bit later, and this has also been protected, patent protected. In this scheme, we have the stabilization reactor first. That's and then we have the guard catalyst named HTM here. Then we have the first H2O step. Then we separated the product, had another HTH step, then did some additional separation, and then we had a so-called HDF step where we used a special catalyst. And with this catalyst, we were able to produce a product with a fluorine content lower than 1 weight ppm. And then you could do the separation, and then you have a jet product that would be able to meet the specification of less than 1 weight ppm fluorine. You could also have hydrocracking involved here. So this is quite complicated when it comes to removal of fluorine here. So I think with that, the take-home message is that, well, we can do it. It's not trivial. You need a lot of different catalysts. TOPSOE has that available, so this is not problematic. The amount of contaminants you have is very, very high, and you have to address that. And we have now a technology so you can cope with the high fluorine content and produce a jet boiling range having a fluorine content below 1 weight ppm. So in short, I think we have demonstrated that we have a technology so we can do it. So we can produce that from that. And with that, thank you for your attention. Here are some acknowledgement to some of my colleagues. And thank you again.
Thank you, Jens. This was very interesting, at least to me, and I hope also to many in the audience. So yeah, thank you both, Daniele and Jens. We have still some time for the discussions. We also have quite some contributions in the chat, and maybe I cluster it a bit and starting a little bit with the more general and easy ones. And 2 questions relate to the origin of the impurities and then also to the nitrogen level. And I think, of course, the impurities are related to the feedstock, but also what kind of molecules you have in these bio oils from direct liquefaction technologies also relates to the feedstock in first place. And this makes many things feedstock specific. So this is maybe one thing, Daniele, you would comment on. And the second thing is very specifically in our project on the nitrogen content. I think what you were showing is kind of an immediate product at the moment that will then still undergo this hydrofinishing, which is this deep denitrogenation that also Jens has showing for his oils. And maybe you can comment on these two things. And you're muted.
Fine. Okay. Thank you. Oh, well, I mean, of course, thanks first of all for all the questions. I mean, very nice. I will try to answer everyone. Yes, and for the inorganics, I mean, as Tino said, yeah, they're basically originated by the nature of the feedstock itself. Speaking of manure, straw in general, they are light and high amounts of inorganics in general, and this, let's say, to some extent, they are found also in the biocrude. I mean, they can be in many forms. Sometimes there are kind of organometallic compounds present, or in other forms. But yes, I mean, the origin is basically due to the nature of the biocrude. So it's something we have to deal with. But in terms instead of the nitrogen. Yes, I mean the level of, I mean, in general, nitrogen is derived from the the protein content of the original feedstock. So it's often, I mean, in this case, we say more manure that will contribute quite a lot. Yes, what we have we dealt with nitrogen content in the order of, let's say, 3-4% in the biocrude, and we were able to abate, let's say, let's say during the hydrotreating, especially in the higher temperatures. The one that represents the most, let's say, the highest, let's say, challenge is the denitrogenation. As I mean, we also saw from TOPSOE presentation, and yes, what I reported in this results was going down to let's say a bit below 1% in weight. 0.8%. This is not enough for, let's say, the jet fuel production. I mean, it's true that there isn't a specific requirement, let's say, I mean, HTL-derived fuels have not been, let's say, standardized yet, but in general, for the existing SAF, I mean, typically we are speaking of values in the order of less than 2 ppm we take as a reference. So it requires a further treatment that, I mean, so is a further, let's say, deep denitrogenation, let's say, hydrofinishing step. Yes, of course, one thing I would like to point out, what I reported is the nitrogen is in the whole biocrude. In the jet fuel, of course, we are seeking this nitrogen in the fraction, in the kerosene range. So there must be first a distillation, and we need to measure it just in that fraction. So it can change a bit compared.
Okay. Yeah. Thank you, Daniele. I think we are a little bit short in time, so but at least I want to have one question also then to Jens. I will answer one, and this is about the green hydrogen. So we see a benefit in introducing green hydrogen here also because you need a lot of hydrogen also to get away with the oxygen, which is not too difficult in technical terms, but consumes quite a lot of hydrogen. And if you take green hydrogen here, of course, it's good for the life cycle balance and so on. But then there are more questions to Jens. And this is on one hand about the different stages. Certainly, these are necessary, but then it's also more specifically to kind of other pretreatment technologies that would come in, and also on the fluorinated compounds. So maybe you can comment a little bit on these questions.
Yeah, I think when it comes to hydrogen, then TOPSOE has a technology called hydrogen bridge. So in fact, you can take the naphtha from the unit and convert that into hydrogen. So it could be in a way be self-sufficient with hydrogen. So we do have a commercial experience where we convert the naphtha into hydrogen. So we don't have to import any hydrogen if we want to hydrogen treat the material. So I think this is the way to go to see if you could produce hydrogen by reform technology, and that's something also TOPSOE has available, and we have a know-how in that area, and this is what we are promoting as a way to produce the green hydrogen yourself within the process.